So welcome everyone to one of our last lectures for our algorithms course. And today we will talk about parsing algorithms. We'll talk about parsing in general, what's involved in interpreting our text, code, right? Some approaches, and we'll see some parsers in action. And also, I guess we'll start with some good news, right? The midterms are actually graded, right? So yay. So, and again, I can tell you the trend is things are getting easier for you guys, right? So it was really hard for you. It was hard to find something bad about your code, right? Again, of course, I'm a realist. Not everybody. I'm sure you use some sort of help. It's normal, right? And so this means, of course, probably next year I'll have to come up with something really tricky to make, right? So next year students, they will suffer a little bit more, right? Yes, because you're so good, right? So yeah. So yes, because it's kind of funny because a couple of years ago it was a problem for about 40-50%. I mean, even the easy problems, people still made some really, I would say, mistakes. Now it's most people skip, they can verify the code, it works, and there are less mistakes. So those who do not get full marks is mostly because of some formatting issues, maybe some lack of comments, and maybe some people it just had some really bad file naming. Like if you submit a file with a text extension, right? Don't make me guess what program it is, right? I mean, maybe it looks like C, maybe it's C++, maybe it's Java, right? I mean, I can tell, right? But if I have to waste a minute or two figuring out, right? That makes me, a little bit less, like you, a little bit less, tiny bit less, right? So, but I know you can do this. You're good, right? So yeah. Again, otherwise, the results were very, very satisfactory for everyone. I'm sure the final product will be similarly good, right, or excellent, right? So yeah, you guys you already submitted, right? So you're fine. Okay, so let's see about today's plan of attack, so to say, right? And we have, I think, at least we'll have one more lecture on string searching algorithms next week, right? I don't think we'll have lectures after that. Maybe if we have a room for it, maybe we'll do probabilistic analysis. But let's concentrate on today's topic. So for today's topic, actually, there's lots of good resources here. The Dragon book is very famous. It's kind of old now, right? It used to be a very scary book, right? So that's something for those who really want a deep dive. But there's some other good resources, right? But there's also terminology book, which is pretty good, which we use here, right? Guide to parsing algorithms and terminology. This one is good, right? Just kind of basic guide. And we will use a Google Colab today, actually, all right? And this is, everybody can follow this if you want. So this should be freely available for everyone. This is what I made, right? So Colab for today. Colab for today on parsing, right? And that should cover most of the information. Add some links there, so you should be able to follow this. So again, so what is parsing in general, right? So we have somewhat, we suspect, we have some text, we suspect there's some structure in it. There's some logic to this text, right? So here you see extremely simple example. You see some digits, there's a plus sign, and there's some more digits, right? And since this is something you learn from like fifth, when you're 5 years old, right? Maybe not such a big number, maybe first grade, right? I don't know, right? But you sort of, it's natural to our human brains. But computers, of course, are not so sure, right? They don't know how to make it. Maybe what does the plus mean, actually, right? It has different meanings. Maybe, as famously in JavaScript, right? You have maybe string addition sometimes. Like one part is string, one part is number, or if it's two parts are string. Like for example, let me do this. Let me open up and where's my here? We'll go here somewhere. Oh, they have I want to inspect. Let me do an inspector. No, or a new line. Maybe here console, right? So all right, there's lots of stuff here. Clear, I think. Yeah. All right. So for example, 4, 5, 6. No, 47. 437 plus 734, right? And we get 1170, right? Okay. Yeah. So, however, right, those who didn't done enough JavaScript know it's not so easy. Like if you do something like this, right? If you do for this 437 plus 734, right? In most languages, this would be a mistake, right? This would be an error. Different types, right? Not in JavaScript, right? So JavaScript is famous, like so. Yeah. So again, interpretation matters. It actually it does string concatenation. How about the other way, right? So it's 437, right? 437 plus 734, right? Same thing, right? So it still works, right? So it's because why is it happening? Because of course, after parsing, there's some implicit typecasting going on afterwards, right? So again, but you can also imagine some language where plus, right? So plus here only has two meanings: adding numbers or string concatenation. But it could be maybe it could be like atomic fusion. I don't know, two atoms smashing together, for example, right? I mean, it could be some really silly example. So again, so there's two parts. One is this lexing part, where we make sense of all these units, these atomic units, to build these tokens, right? So we build a numeric unit, token plus token, another numeric token, and then we supply it to a parser, and then we have a question of how do we represent this, right? And you will see that most commonly it's represented as a sort of tree-like structure. A tree-like structure. Why? Well, because it makes the most sense, right? And it also leads to nice recursive parsing later on, right? Making sense of it, right? So again, why should you care about this, right? Again, you probably say, okay, I'm never going to write your own language. Well, you'll see that actually by learning some basic ideas, but hopefully everybody can hear this, right? I hope everyone can hear this. Is sound on picture okay? I'm just curious, right? Maybe it should be. I assume transcription is okay. So I assume, yeah. So I assume if the mic is picking up my voice, so I assume the remote team is able to understand me. All right. But so why should you care about this lecture today, right? I mean, so again, if you ever gonna have a specific problem, or you might actually, with this knowledge, if you go in deeper, right? You could take, of course, whole course on this. Maybe some of you have, right? You could create your own language, so-called domain-specific language, possibly, right? Meaning it's tailored to your problem, right? Again, most likely you will not implement compilers, unlikely, but it's possible, right? Very few openings for jobs there, but it's possible, right? But also, it can lead to general, of course, skills like debugging, optimization, but also last thing, right? This comes from me, but also I know other people who have this experience as well. It's parsing strange input, which is not necessarily a computer language. I mean, it's not a programming language. Just could be some JSON, but maybe a badly formed JSON to some strange, somebody's strange, bad idea of JSON, maybe XML, or maybe something worse, right? I don't know. Some other things which don't have your basic parser, which is built into your language, it doesn't work or doesn't work properly. So this is where your knowledge of parsing, you see, okay, I know how to parse things. I could probably do this myself, right? So this could be a good tool to add to your tool selection of tools. So that's the main idea today, to have a new tool, to think about the problem in a sort of different way, maybe. But okay, but let's start with something really simple, right? Let's make a arithmetic parser, right? I'll make this bigger, right? To parse and evaluate, meaning process or interpret some very simple arithmetic expressions. We'll start with the simplest one, just addition. Maybe we'll add subtraction, but maybe then on, hopefully by the end of lecture, we'll progress to something, to more powerful, right? So I'll be using Python, but this is basically almost like pseudocode. I'm sure even if you don't use Python, you'll be able to follow this. So we have a eval. Python has this built-in function eval, which basically, but we will try to emulate this, right? So eval basically takes whatever you supply, right? It tries to evaluate, right? So it's kind of dangerous because you don't control the string, right? Something could, if you have a user supplied, don't use eval in production if you don't have sanitization, of course, right? It's a very dangerous function because you could do anything, blow up the world, right? So, but it works. It's very convenient, right? Because basically it will run whatever you supply. So this means Python interpreter will actually parse it, right? It will do alexing, it will tokenization, it will build the parse tree, and actually how to evaluate according to the rules of Python. And you're not going to be shocked that you get 18, right? So you can play around, of course, you can try your own eval, you can do whatever, right? It will work. Even if you do a print or something, it will try to eval anything. It's legal, whatever Python is in there. This is something useful. Again, sometimes it lets you do some very powerful things, but generally, of course, eval is not used in actual production code. So that's something I should mention, right? Yeah. Generally, eval is not used in production, right? Code due to safety issues, right? But okay, we are learning here. But okay, so I'll do my own. So you only saw this upper part. We have to do two things, and right now it's very simple. We will have to tokenize, meaning we'll do this lexing step. We will separate the code or string, right, into tokens. This small, so atomic units, token, smallest unit, we can process. So here we can sort of, take the easy way out because we know Python has a string split operator, right? So assuming you have a space between the units, it's trivial to split by white space, right? There are other ways to split, of course, but we'll split by white space right now. And we get tokens. How many tokens do we get? Well, we have 3 numbers, and we have plus and plus between. So I hope you can imagine that this stage, the tokenization stage, there is no check on is it valid input or not, right? It just spits out tokens. Of course, there could be invalid tokens, maybe like an exclam, but in this stage, these tokens could be anything. I mean, there's no extra step. So this is very loose. Note there is no real check for valid. What makes a valid token here, right? It's just tokens, right? So there is a sort of like a line between tokenization, right, and actual parsing, right? Where do you decide what's valid, right? So usually it's done together, of course, part of the one process. So the line is a little blurry at times. Okay, but you're clear. We have some tokens, units of something, right? So how would you add this? Well, you write the loop, right? Well, we want to make it, well, the ideal is, the dream is to do this in one pass, linearly, right? Multiple passes, but let's see, can we do this in one pass? Well, let's think about, can we do it? Why not, right? Because we only have addition. So question might be, do we need to store any information? Well, this is a good question, actually. For now, we'll be sort of like really naive, right? And this first attempt is not going to be great, right? But it should work, right? So we go through each token, right? We have a loop. So that means linear complexity, right? Just a simple loop. And of course, we have some checks inside. So we again, is numeric. Python supplies this, but of course, we could have your own method, but it should be fixed cost, right? Should be O1, right? We check also here already. If it is numeric, we do casting to integer, right? Otherwise, if the token is plus, right, we skip, right? Otherwise, we say if it's not numeric and if it's not plus, we already have some validation checks, right? We only accept numbers, right? That's good, and we only accept plus sign, right? So that's only or language has a very limited vocabulary, right? Just numbers and plus, right? So but okay, and will it work, right? So tokens. So we should get 18, I hope, right? We have a result, right? This is not a function, but it's just some code, right? It's code cell, and we go through. We have add, right? And well, so the question is now. So without going deeper, there is a problem with this code, and I can give you a hint. It's a little bit too liberal, right? So what's the issue here, right? Well, do you see the issue? Well, the issue is already implicit. Well, we are going through our tokens and we're just sort of eating them. That's a normal term, by the way, eating tokens, right? In parsing. But we are always adding, right? But notice this code here. This code here is this. It's a little bit loose, right? Why? We have no knowledge of what happened before, right? So what's the issue with this code? It means that I can show you an example, right? I'll give you a different code. I'll show you a code example. So weird numbers, right? Weird input, right? Could be something like this, 50, 60, 70, I don't know, 75, right? So will this work? Hello there, right? So if I am reading this code, this just came to me when I was looking at my code and saying, okay, yeah, this is too loose. So what's the issue here, right? Will we check if it's plus? We only check if it's an integer. So this is like we have this addition implicit, right? Tokens, right? And right, tokens again is weird input tokens, right? Input split, and I can of course split like this, doesn't matter, right? And if I copy this, right, you will see this, right? And this is again, I should make the function for this, right? So we'll see. Yeah, 173. So now you see the problem, right? Now you see the problem. Well, it's just like a language. I mean, it could be a powerful language, right? If it says, okay, anytime you have a number of a string of numbers, you need to add them together. I mean, there are some languages, right? Some constructions where this can be very handy, right? But especially if you're supplying like a sum, you're supplying a list and you want sum, right? I mean, this could be handy. Well, this could be, this above could be handy. Could be handy if you try to implement a sum over an iterator, right? List, tuple, etc., right? But it is not, however, it's not quite what we want. However, it is not quite what we want, right? We want to use this plus also as sort of safety check. So let's fix that. So in order to fix it, what do we need? We need some memory. We need to store some state. And again, to make it very simple at this moment, let's just use simple Boolean for now, right? We will use last as number, just simple Boolean, right? So again, this still we're only dealing with addition at this moment, right? So we have an expression, right? We're going to tokenize it again. We have different ways. We have different ways of tokenization, right? Here we use single white space, right? But okay, again, we have a starting result, or actually, I should probably call this. Could call this accumulator, or ACK for short. That's also used, by the way. So last was number. We assume when we start our expression, we don't have a number, right? So it's false. Makes sense, right? And again, we use same approach, but now we have a one tiny bit of memory. We have at least one Boolean that says, okay, did you use a number before? Right, so now we can check. So now we're not going to be able to do any shenanigans with, just numbers, right? That's not going to fly anymore. So it should, I hope you can see this code, I hope, right? Can you see this, right? Okay. And again, it still should be very easy to follow, I hope, right? I mean, it's just a loop and just if statements so far, right? And basically, we check our tokens, right? So again, tokenize, one liner, and we go through, right? So it's basically evaluate. Actually, it actually includes everything in once, right? So it's single loop, yeah, one pass, single pass, and it should work now properly, right? So let's try this. So now let's try this with some bad values. So now let's try it with some bad tokens, right? Yeah. So let's see. So print. So let's try to break this thing, right? So how about this one? Minus. So this approach here, well, it's the problem will be that is numeric does not allow for negative sign, right? So this will be an error, right? A value error, invalid token minus 1000. That's good if you're building. Well, it's good and bad at the same time, right? It's not good because, well, you might say, okay, maybe you want to allow this. Maybe later we can allow this, right? But for now, it does not allow it, right? That's fine. How about how about a bunch of numbers? How about a bunch of numbers, right? So if I was building unit tests, I was doing some testing, so again, we will do numbers. I can probably get it from here. I'll just copy paste, of course. Dangerous. Copy paste is always dangerous, but let's do this one. The weird input, right? So this should also fail, right? It worked before, but now it should fail. It's value error, invalid token, 2 numbers in a row not allowed. That's good. So we were able to get the errors we expected. Again, so your checks, you could do assertion checks, it would work. Okay. All right, so our addition, I mean, I think everybody could do this. Like I said, it's 15 minutes, 10 minutes of work, maybe 20 minutes, I don't know, but simple loops, easy. Even if without language models or anything, right? But now let's do as subtraction, right? Subtraction, subtraction. Okay, which was correctly spelling? But okay, right, subtraction. All right, so now we need a little bit more memory, right? We need to have a little more memory because we have to keep track what we did last, right? Similar to addition, but now we need to keep also, we have 3 types of tokens, plus, minus, and numbers, right? Again, the general big idea is that the plus and minus sign doesn't matter. It could be, it could be emoji or something. It doesn't matter, right? It's just a symbol, right? But we are going to have internal representation, plus or minus, right? And then we can convert back to actual minus and plus, right? Again, it seems silly here because we already know what plus and minus does, right? But in general, this is the approach you take because you don't know what token, also these tokens, right? These units, they can have different meaning, right? Depending on context. Right now, we don't have context free, right? So it's very easy still. So also at this stage, I'm already going to have a separate tokenize to separate the steps. It's still extremely simple, right? But now already you can have your own tokenization. You could modify this to maybe make it more, maybe more stringent. Like you could add some things. Maybe your split doesn't do what you want. You could have like extra checks. But again, tokenization only returns a sort of like a structure, a collection or a iterator of these tokens, basically, right? That's all it does. It does not check whether they're actually, synthetically good tokens, right? They're just tokens. Okay, now evaluation. So I have some debugging, added some debugging code on. Again, we have result. Again, accumulator would be nice, but token types. And this is also just for documentation for you guys, because it would be nice to use enumeration types. Languages like support enums. You would use those, right? Because why? Because the strong types would let you avoid the errors. You don't mistype or something, right? Python is too loose with this as well. Okay, and now we'll use a hash map, a very tiny hash map of 2, dictionary, right? Which is, the 2 keys, plus and minus, and they map to plus and minus, right? So, and also we don't want to allow 2 numbers, and we don't want to allow 2 operators in a row. We will consider that an error, just like before. So how do we accomplish this? Again, loop, single pass. And now we have the logic, and there are a couple ways of doing it, but we have to do 2 checks. We check whether it's a valid. If the token is invalid operators, right? If this token, right? Well, we check first. So this means we check whether it's plus or minus. This is a quick check. Again, hash maps are good, right? Keys, hash nicely. So, but then we do it again. Why? Because we need that, we need to have this memory. We know what we did last. We know what we did last summer. We did, half a millisecond, half nanosecond before, right? We check the previous token, right? So two tokens in a row, it's an error, right? Not a valid language, not for our purposes, right? So then we assume it's valid, right? But now if you have an operator, do we have to do anything? Well, no, because we don't know what's going to come after, right? We don't know what kind of number. We don't have to do anything, right? Because we just have an operator, plus or minus, right? However, we don't know what we're going to do next. So what do we do then? Well, yes, so we go back to the loop, right? We keep going, right? We have more tokens process, of course. By the way, hopefully maybe some of you who are attentive, there's already a bug in this code, by the way. Maybe some of you will be pointing this out to me. I want to see if you can find this for me. But okay, now what we do is we try to convert it to integer, right? And this time we use a try except because it's easy, right? So we try to convert it. If we fail, this means we did not get a number, we did not get an operator, we got something, some garbage which you don't know how to process. And again, this is a room where you could do also, if you are very liberal, I don't know, you're writing HTML parser or something, right? Where you want to let people make stupid mistakes, you maybe just say, okay, it's not an end of the world, we'll just ignore it. That's completely valid strategy, right? Of course, we could, right? Note, we could just ignore invalid tokens. That is fine approach sometimes. Right? So, but okay. But basically, what we do is we check is the last token plus, right? Because we converted. Look here, right? We do this here. Note, yeah, we use the dictionary, right, to get the actual the name, the symbolic name for operators, right? So basically, get this plus and minus here, right? So we have plus and minus. So if you get a number, we know what to do. By the way, I noticed something else interesting. We could have done this here. There's two, the plus and minus, right? If you have a plus, right? Last token is plus. I wonder if there is actually an error here. Let's see, 50, 60, 70, right? Yes, there's two. I found two errors, actually. There's two errors in this code. So maybe we can see this in action. Why is that? Let's see if we can track the errors. Well, let's do something really simple, and you'll see the problem with this. Maybe then you can do this. You can help me fix this error, right? So 50 plus 60, how much should be 50 plus 60? Well, that's a trivial question, right? 130, right? So what I get, what do you think of the first one? Any clues? What will be the answer? Where's my mistake here, right? Maybe you can see this already. What's going to happen? Any hypothesis? Well, we'll see this in a moment. Any ideas? What will happen? Can you see this code? This code, basically. We have some tokens. We're going through them. We try to convert them to numbers. We have minus plus operators, right? But there is a bug. Well, actually, there's two bugs, but this one first. The first one is a critical bug because it gives us incorrect results. Well, let me run this, and then you'll see the error immediately, right? I got 60. So what's happening? Yeah, it's skipping the first value. So let's see why. So let's do a little debugging. Hopefully you can see this. Well, the issue is this. We had none, right? We don't have the first token. So we check if the last token was plus, we add it, right? But in the beginning, there was no plus. So, yeah, it skips the first. So there's an extremely easy way of fixing this, by the way. A really simple step. But how can I fix this? Any idea? Yeah, but basically, there's no point putting none. I can do a little cheat and put plus. I'll pretend that the beginning was plus already because I need. Yeah, because of course I could do it here, but the thing is, this would not be maybe correct to add it here immediately, right? Because I don't know yet whether the first one is. I don't want to have separate to check if the first one is value. We'll have a loop for that, right? So let's do a little trick, right? To pretend that this is actually, right? We'll do this plus, right? So this little trick here, right? This should solve our first problem, right? So to add the first number, we pretend, or we add a fake, we add a fictitious or fake, right? Fictitious. I can't spell again. Fictitious. I can't spell the plus operator, right? We still this way we will verify, right? Whether the number, whether the first token is number, right? Okay, so that should, hopefully this works. I think it should, right? Let's take a look. And indeed, 110. By the way, again, nobody's correcting me. My math of is not. I'm not 130, 110. 60 plus 7 is 130, right? I'm not calculating today. I guess I must be half asleep, right? So yeah. All right. Thank you. Right. So now that we have solved this first problem, let's see if we can solve the other problem which I just thought of, right? So it seems to work. It works on negative numbers. See, 50 plus 60 plus 70 is what? 180 minus 100. Yeah, it works. All of these work, right? We can see that, in the verbose mode, we can see the tokens looking pretty good. But where was the issue which I saw? Another issue where it's not quite, it's still a little bit too liberal. Let's take a look what I didn't like here. So we have a number, right? So we continue. We have a last token is valid operator, right? So if last token, so if it's two valid, so it's two tokens, it will fail. Now if plus minus, yeah, it's still, there's a problem. So if it is not a valid operator, right, this means it's supposed to be a number. So what happens if you put multiple numbers, right? Well, I think just ignore them, right? I think it's not going to be a number. So it's still not checking multiples, right? So let's try this. I think we can do this one more, right? So still not raising error on multiple numbers, right? So let's try this. So print, evaluate, tokenize, right? And let's do something like this. So 50 plus 60, and then I have 100, 200, 300. Let's see, do we get error? Let's take a look. I am suspecting that we'll have 110. Why? Yeah, because what happens this, the last token, right? It checks, is it a valid operator? No, it's not gonna be last. If it gets a number, it still try to do something basically, right? So if token, right, it tries to raise the token. If it's not minus, it will be a number, right? And it'll do nothing. Let's take a look. Oh no, that's good. Two numbers in a row. How did I get this actually? Let me see. There we go. Right. Oh no, we do have a check. Okay, so that's good. So we do have the extra check. Yeah, I did add the check here, right? So no, everything's good then. Okay, like I thought I saw something else. Well, if I forget, if you find another error, meaning it seems to work, good as far as plus and minus goes, but maybe it's still too loose. Maybe it still accepts some garbage. Again, you want to be pretty strict, right? You want to let the user know immediately that there's a problem with your code, right? Okay, so now we have fixed it. Again, so this works. Good. All right. So now everything works properly. All right. Now, all right. What is happening? I'll say later. Yeah, GitHub. I'll add the change here. We have some fixes. So now we can go in. Now we have built this very simple parser. Let's see what would be involved in writing something much more difficult. right? I'll just give you an outline. I'll show you some code. I'll show you some code samples, actually, how you can do this, right? I've done this before, so you should be able to follow this. But it won't be, it could take maybe a couple hours, so it's not to go deeper into the code. So, but basically, this stays the same. Tokenize, right? And parse the tokens, right? And then, of course, you do something with the tokens according to your logic of your code. But now, for larger, if you have lots of rules, if you have a very complex grammar, C++ or Rust or something like that, right? Well, doing this like by hand rules, you would not be able to write this, human lifetime, right? You need some better way of encoding this syntax, this grammar. You need to encode the grammar. So let's go this deeper. So you have this lexical analysis, right? You convert these raw characters into tokens, sequence, of course, atomic elements, and then you have this. You build a parsing tree. And actually, now let's look at this. There are two types of trees in terms of parsing. One is a so-called regular parse tree. And what's the difference between those two? If you're adding two numbers, 10 plus 21, right? Well, here you include the actual token for plus. But if you think about it, you don't really care that it's a plus, right? Or it's maybe emoji for plus, or maybe it's a smiley face, or maybe it's a, English letters, and they add something, right? You only care that the operation actually reflects this. So that's why usually the parse tree at some point is converted, maybe immediately, it's converted to an abstract syntax tree. It's called AST, right, for short. Basically, it says sum, right? How that sum is represented in actual language, you lose that information, right? You lose all the white space, you lose everything. You just have it. Well, you need the numbers, right? Those are concrete, but you need some operation, right? You have it defined somewhere, right? How the sum was represented by what means in your language, in your grammar. At this point, that information is lost, but it's not relevant anymore, right? So that's like that's from this you can actually start evaluating the results. Okay, so also I mentioned there's some terminology here on there's a compiler versus interpreter parsing, right? In the compiler, well, what does compiler generate? What do you get in compiler? What's the end result of compiling? Excuse me? Yeah, well, compile language like a C++ or C, or I don't know, Rust or. Yeah, what happens? What do you get when you compile something in those languages? Yeah, you get machine language, you get machine code. Well, maybe it's an intermediate code, but you get something you can run immediately, right? So that means for compiling, well, you could afford to go back and forth because your end goal is to generate the best machine code there is, like the most efficient. You maybe squeeze some operations, like there's different flags. You ever use the GCC or any of the compilers, right? There are flags, you can have lots of settings, with error, with extra error reporting, maybe warnings and so on, strict mode, and so on and so on and so on, right? So this means the compiler step, right? It can do it back and forth, could have very, very complex. With an interpreter, right? That actually, in a way, it's easier because, well, but it's also more challenging because what you're doing is you have interpreter, it has REPL loop, right? REPL, you have interpretation on the fly, right? It's a live code. You write something 5 plus 5, right? If I do something, where's my, I'll do here like to slide, inspect again, right? Console again, clear, right? Clear function, right? So if I do something like this, 5 plus 5, right? This is interpretation, right? So this means the JavaScript engine, right? It has to interpret this on the fly, in a live setting, right? So that's challenge. In some ways, it's more challenging, but also in some ways, well, there's some different challenges for doing this, right? But of course, there's also hybrid approaches, right? Just in time, all kinds of different things. But again, so it has to adapt to partial inputs. Like it's like you're typing, in Google search, you type something, right? It's also a way of parsing, right? front end, right? You know, for Google search or any search engine, he has to do some parsing. It's not a language, right? But it's also a way of parsing something, right? So, but in order to do something more, how should I say, bigger, to be able to handle bigger, more difficult languages, you need some formal way of describing these languages, right? And there is actually something called Chomsky hierarchy, right? This Chomsky is actually a very famous person, still alive, actually now mostly in politics, but he was a language theorist in 1950s, 60s. And so he came up with this hierarchy of grammars, right? So we have so-called regular grammars. I don't know if you've taken any, have any of you taken automated theory? Anyone? Any automated theory? Not yet. Okay. I'll add a link to this, all right? I'll add a link to this automated theory. This used to be a first class in computer science, and usually half of people fail this, right? And it was so I don't know. I guess it's not around anymore, not as much, right? So yeah, so it's kind of like this, right? So yeah, it leads to Turing machines, which we all use all the time, right? But it's very interesting theory. It's like a hardcore computer science. So let me add this, right? It's part of, right? Where's my here? Grammars have a direct relation to automata theory. There is, yeah, there are different grammars that correspond to different automatons. Okay, automatons, right? So, okay, so that's something to explore if on your free time, assuming you have free time. I don't know, you have free time. So, so again, I'm not gonna. I'll just list this. There are different strategies how you parse it. We'll do a top down from the top right. There are some key parsing algorithms. Again, if you don't have recursion, basically we have a linear performance. There are other approaches, right? You can have actually a cubic performance, which is not very good, but it's, well, it has less restrictions, right? So so if you do your own parser, maybe recursive descent, right, which we'll be doing in a moment, it'll be fine, right? The good news is you don't, if you learn to describe the language what you're trying to parse, you don't have to write your own parser. They are so-called parser generators. Basically, these are programs that take your description of the language you're trying to understand, and it will generate code in another language. Could be in C, could be in Python, could be in JavaScript, could be in C++, you know, Rust and so on, right? So it's kind of cool. So if you want to write your own language, programming language or human language, you don't really need to write your own parser, right? Because writing parsers, efficient, performant parsers, is quite a challenging task, right? So you can use these tools. Antler, by the way, this guy, he worked on this, on this tool for, like, I don't know, he is a professor at US University of San Francisco. He worked for so long that eventually Google hired him to work on Dart language. Anyone use Dart? So he works on Dart. It's for mobile applications, basically, right? So, but he built this really cool tool. Even the guy Guido who invented Python, senior guy at Twitter, and so on. Everybody, people who wrote Objective-C, right? Everybody has high price for this tool. But the idea is this: you describe the grammar, and it will spit out the parser for you. Very cool, right? So it's something like this. It looks like something like this. You can play around with it. So you can see in this example, I don't know if you can see it very well. So it can parse. This is what describes this type of syntax, and it will parse it. I mean, here you can see how the parser can also create this like definition. What's the definition? So it's function definition, probably in this case, right? Stat, right? What does stat means here, right? So stat1, stat2, right? Meaning probably static variables, probably static meaning, right? And of course, how do you evaluate, right? So A is expression from expression 3, right? And you also have expression X and Y together, right? So it will generate this tree. Pretty cool, right? So, but let me show you how you would build something more complex. Just a short introduction. So, again, we'll split it in two parts, right? So, first we do is you need to look up something called EBNF. It's a way of describing. It's been used since late 1950s, 1960s for like 65 years. All programming languages have some formal way of description of this in this type of form, or something similar, maybe use also PEG, maybe, but EBNF is the most standard, basically. So you say you have left side is basically you define in some non-terminal symbols. What does it mean non-terminal? Means it doesn't have a full definition. It's like a variable, kind of like a variable, right? On the right side, you might have some rules of production. You have rules of production, meaning how do you make out of something, what makes this left side? On the good news, on the right side, you could have, well, sometimes it allows you like recursive definitions, sometimes very powerful. Some grammars also you define it in terms of other non-terminals, but also how do you get to something useful? Well, at some point, you also have to define terminal symbols, right? You use that, you are allowed to use terminal symbols. So in this example, and this makes bigger because this is kind of the syntax, right? Look at this here. In order to come up with an integer, right? First of all, you define a digit excluding 0. That's 1 to 9. So why do you do that separately? Well, because, well, first of all, we can now define actual digit using 0 or any digit using 0. So that, well, that makes sense. So why did this grammar use this? Well, because how do you define a positive integer? You don't start with 0, but you ignore the zeros. So that's why we say it's any digit excluding 0, but we don't want to, I mean, we don't want to do this over and over, right? It's like a variable, it's like a constant, right? So we use that, and then what does this mean? This is like in a regular expression, you know, optional, as many as you want. 0 digits or 5 billion digits, sure, go for it. It's an integer, it's a positive integer. How about a universal digit? I mean, a universal integer definition. That's easy. It could be a 0, right? That's true. Then, how about this syntax here? This is, again, this is optional. Minus is optional. And then you have a definition for positive integer, which we already know. It starts with non-zero, right? And could go on forever. And that hopefully makes an integer. You agree, right? It's an integer, right? Makes sense. I mean, it's easy to make some mistakes with this, right? But now let's move on to these parts here. What's going on here? So basically, we are describing grammar for language which only allows 4 operations, plus or minus. So why do we add plus and minus in the same on the same scale and on multiplication and division separately? Why? Why do you think? Because, well, because in regular algebra, regular math, we use these are, you know, have same precedence, right? So it makes sense, right? So what we say is that expression, right? This is our stop term, right? Expression is defined as what? As a term, and possibly plus minus another term, right? Because this means that plus and minus will be done last. So, well, but what's term? Well, term could be a factor, right? It could be times or division by another factor, right? But factor, it could be an integer, or it could be something, some expression inside parentheses. So we have support for parentheses as well. Okay, so now I'll show you something cool. You can go to this link here, right? And play around with this. I hope it goes through. Is this the correct one? No. So it's the 5 plus 6. Let me see here. Is this the correct one? Oh, yeah. So notice something interesting here, right? It does not have space. White space is not allowed in this language, in this particular language. So it actually is very strict, right? Very strict. language, right? So 5 plus 6, right? That's valid. Space is not valid. An error, right? So how about times? Well, it's an error immediately. Why? Because I did not add a closing integer, right? If I start to multiply something, I have to finish this, right? So add 10, that's valid. How about this plus 5 plus 4, that's valid, times 10. Again, valid, right? And again, division invalid, 2 valid, right? Division by 0, well, it's valid because we allow division by 0 in this syntax, right? Again, the grammar does not check for sort of semantic mistakes. Because, let the parser later on, after parsing, when you actually evaluate, handle that division by 0. I mean, we could handle it here as well in a grammar. We could say, okay, you are not allowed to divide by 0. But again, if you think about it, if you can add variables later on, how do you make sure? Again, at some point in eval, you can't really handle this in a grammar, the division by 0 type of errors, right? So you could handle some. Okay, so you can play around with this, right? You can play around with this grammar. There are other tools, right? So just here, you can play around with your own. Play around with your own grammar. Here, grammar. Syntax grammar here. There are other sites like that. Yeah. Okay. So you can test your language. So one challenge would be maybe add device support. Easy to do, actually. Again, not something you do every day, but you could. But okay. So I want to actually we'll go. I don't want to wait too long, right? But you can play around with these. But no. So okay, we have grammar, right? Something like that, basically. And here I cheat a little. I cheat here. I basically, here I sort of, skip the full definition of integer, right? As above. Yeah. Okay. But so what do we do? Then next we have tokens. Right now, again, this is just one way of doing it. We're going to use regular expressions. Regular expressions, of course, those of you, I'm sure you use this. They're very good for parsing certain things, not everything, right? There's things you can't parse with regular expressions. They're not Turing complete, right? But we generate token spec. So basically, it's a tuple token. What type of value? Type value, type value, type value, right? Bless you. So basically, this is how we are going to extract the actual tokens. So this is more powerful tokenizer, right? We'll have each have a list of tokens and what it is, basically token and value, actually, right? Token value, type value, type value. Okay, so this is kind of cool. Also, notice the yield, right? Those of it in Python know what yield does. It's like a generator, basically, to let you have. It doesn't give you all the values at once. Why? Because you're going through them one and one. Maybe you don't need. Maybe you have a huge program and you don't want to actually tokenize everything, right? So this lets you handle this. So it also has an EOF, end of file token, could be useful, right? Because you want to actually end this whole thing. Now AST is basically just to say that we are using an abstract syntax tree, sort of. So we'll use the inheritance for that, right? It's not really, strictly necessary, but it kind of makes, kind of tie these things together. And then we say, okay, we define a binary operator. What's a binary operator? Meaning two sides. You have, plus, 5 plus 5, you have two operator, operator on your left side and right side, right? Could there be other operators? Sure, unary, right? 3 plus plus, I plus plus, right? That's a unary, right? Operator, right? Or maybe a square root operator, function. That's also unary, that's a unary operator, right? So, and then I think this is pretty nice code. So parser, we have our tokens, we have an iterator. So notice another thing is we take the next token, right? and we eat it. We eat the token, right? These are methods for it, right? So we're going to define token, but we check whether this is allowed, right? We expect that this, right? If we get something this and we get something not correct, right? Then we say, no, this is wrong. This is not wrong, right? Cell tokens, this did not work, right? So if self current token type is token type, right? We can eat it if it's, if it's not allowed, right? So how do we parse? Let's look at the parser. Basically, we have a node self parse expression. So, well, this means we have delegated this to the parse expression. So now we get, I think, hopefully to the parse expression, right? So notice how neatly this will work. Parse expression first, plus minus. However, if we get, so while we have plus or minus, we parse it. Then maybe we have to parse the terms, right? At some point we parse terms, right? We have a multiplication or division, right? So we eat those, right? And then we have factorization, right? And those are the most important. So it's like we get down to the parentheses. So those will be processed first because parentheses, right? They have the highest priority, right? In this, pretty much most normal arithmetic language. And then how do you evaluate? You have this tree, right? You have this whole tree built up like this part of here. Something like, well, but much more difficult, right? Much more, let me try it like syntax tree. Abstract syntax tree example for arithmetic. Let me see here, maybe images. Yeah, so something like this, right? Yeah, this looks good, right? Ruslan, actually, this guy is pretty cool, actually, yeah. But this guy, I think, yeah, I mentioned him. This, I think, something like this, right? So this is what you end up building. You have a tree, right? So 2 times 7 will be evaluated first, all right? So you end up building something like this. All right. And now we'll check. Oh, no. Yeah. Okay. Yeah. All right. So, so let's check if this works. So again, the beauty of this is if you set up correctly, you'll see this with this type of scaffolding. You could build your own parser. Really, for most things, you see the priorities correct. Really, so the actual work, that's how it's like a main function, interpretation function. It's only a couple lines. Tokenize, parse it, right? Parser, right? Apply, create the parser from token, make a tree, right? Abstract syntax tree, and then of course you evaluate the abstract syntax tree, right? So, so notice something. So what kind of function is this? What kind of function is this? Well, what type? What is it doing? It's calling itself. So it is recursive, of course. So why recursive? Because that makes things so easy, right? Again, you could, of course, reminder that recursive functions you can always emulate with a stack-based approach, right? But this makes a very easy evaluation, right? And of course, you assume you're not going to work on stack phase. I mean, no matter how difficult your huge program is, I don't know, 100,000 lines, you should be able to build a nice tree. And I mean, you should be able to have enough stack space, right? I don't know, Windows source code or Linux source code, I don't know, 100 million lines. I don't know how much Windows is, right? I mean, theoretically, it could be bigger, but of course, it's done in parts. And again, there's all kinds of ways of optimization for that if you're compiling something. But yeah, generally, interpreted language, no problem. So this is for simple, but of course, this is for simple cases, right? So you check, right? If it's a numeric, you get the value because it's already just nothing else. If it's binary operation, you need to evaluate left and right side. On this way, you check, is it left, minus, right, or division, right? And that's it. So extremely simple, but already we have a full interpreter for arithmetic, basic arithmetic. So if you want to practice, you see if you can add like a square root operator or something like that, maybe add that. A unary operator would be interesting challenge. All right. So last thing we're gonna finish in a moment. Last thing is I added multi-line support on variables. Right. We are already getting somewhere, right? So grammar, right? We have some variables here: program, statement, assignment. So we have assignment. So what do we have new? We have equality, right? We have new token equality. And what else do we have? We have identifier. And what do identifiers is basically start with underscore. Well, it could be a dollar sign in some language, right? And of course, English letters. I mean, assuming, of course, you can also add Latvian letters or Spanish letters or French letters or, Japanese, right? But for now, we use just the English. And what happens now? So we have AST, binary, numeric, and we also have variables. So what do you do here? You basically supply the name, and that's it basically, right? It's in a class variable, right? You store it, right? So it turns out it doesn't really add much extra. So some things are really easy to do this with this type of parsing approach. Like variables, easy. You just save them, right? So check this out. So what changed? Well, we have our integers, we have identifiers, we eat them, right? Left parenthesis, we have right parenthesis, right? So if you can't eat them, right, there's going to be an error, right? Invalid syntax error. You get syntax checking already. And now with variables, if it's a node value, if it's a variable, if there's a node name in environment, right, we supply the environment, meaning it's a scope. We already provide some scoping already here, right? We can save it. Again, you need to decide how you're going to save it, but you save it. And then you basically do it. Left, right, you have this environment, context, basically. And same thing happens. So let's do, we have an interpreter, we have a multi-line support, and we have some variables now already. So we add split lines, right? So we support for multiple line programs. That's good, right? And we do the match. If you don't have any tokens, right? Interpret, right? We have tokenize, right? Expression, right? So this is our test. X equals 5, X times 10. We should get 50, I hope, right? Last time I did, oops, not like that. Let's do it. 50, right? How about two variables? No problem, right? X10, right? And it works. Let's do one more. Since I'm feeling dangerous. Let's do this. Let's do a bigger one. Let's do program equals, right? Yeah. So A equals, I don't know, 10, B equals 20, C equals 30. Now, of course, you might be saying, what happens if I do this something here? Well, yeah, it will fail, right? Of course, it should fail. But so we'll do this. So A plus B, right, times C, right, plus 1,000, right? Right. That should look okay. So how much should it be? It should be 900, right? 30 times 30 is 900 plus 1,000 should be 1,900. I hope. Right. Let's add the plus 125, right? So 2025, right? I hope so, right? So let's do that. And of course, let's run our program. So print, interpret, and program, right? Or little tiny program. I can type R. Okay, yeah. All right. Let's take a look. 2025 works. Super. So yeah. So really simple interpreter. Well, of course, is this a Turing complete language? No, because we're missing if, right? So if you think this is interesting, actually, I highly recommend this book, right? It's called Crafting Interpreters. It's free online, but also you can buy it. Really nice drawings, right? Really covers all the basics, and also it goes into something more advanced as well. It starts with a basic approach, something like I did in the class, but much deeper. But also goes into more advanced way of parsing in the second part. And also, I think has a GitHub support, GitHub repository for the code. Really beautiful book, right? Has high reviews. So I really enjoyed. If I had more time, I would love to spend more time with this book. Real fun. So this guy also, like I told you, he works on Dart language, right? So this is really nice. So this guy works on Dart. The other guy works on. Does he also work on Dart? Let me see this. So he works on Dart, right? Oh yeah, he works on Dart. How about the other, the Antler guy? Did he work? I don't want to mislead you here. He works also at. He works on. He's tech lead at Google. So hey, he's not a Dart. He's actually like just basically, authority there at Google, right? Kind of nice gig to have. Nice job to be a tech lead, right? Meaning you can do lots of different things, right? But you don't actually have a full you don't have to write dashboards for ads or something, hopefully, right? So okay, so what's the takeaway from today? So if you have some non-standard text, this is where you might want to consider writing your own parser. If you have standard text, well, if you can come up with a grammar, right, you can generate your own parser using these tools. So eventually, if you're going to work on programming, coding, you will encounter some weird format, which is not, you have to create, parse it. You have to interpret it somehow, right? And again, you will be able to, either you'll have to do some sort of parsing. In the worst, easiest case would be just some regular expressions, just tokenization, but maybe you'll have to also add this actual extra step for evaluation as well, right? So I recommend you check the resources today, do the quiz, and I will see you next week on string searching algorithms. Yeah. All right. Thank you, everyone. I'll see you next week, 4:30 again. See you guys next week at 16:30 again. Hope today was interesting. On this recording, I'll stop.